Welcome to the Philosophy of Science lecture. Last unit we spoke about different forms of scientific argumentation, especially in the last part of the lecture we spoke about the relation of induction and abduction. Abduction, or inference to the best explanation. I told you that the most important function of abduction in science is to infer from observed phenomena to theoretical models which contains what we call theoretical concepts. That is, concepts referring to properties which are not in the space of the observation of the observable properties. So they are not directly observed or measured, but they are indirectly introduced and posited in order to explain the observed phenomena. And my example was the Newtonian abduction, right? And in physics, in classical physics, you have this nice division, the Newtonian abduction from the observation of the movements of physical bodies, in this case planets. They move around the sun in elliptic orbits. So the abductive inference from this data about the velocities, positions, accelerations, trajectories, to a force model. So the explanation Newton gave was in terms of the Newtonian force law, and these Newtonian force laws could so wonderfully explain these movements, not only of the planets, but only of the bodies on our Earth. And so the abductive conjecture is Newton's force laws, because they are empirically so successful in explanations and predictions, these force laws are approximately true. So this is abduction to a theoretical model. And given this notion of theoretical model abduction, or abduction in science, then you can really depict the relation between epistemic induction. You recall from the last time what I called epistemic induction, induction over the empirical success rates of theories. You can explain the relation between epistemic induction and abduction in science as follows, right? First of all, you have a couple of competing theories, for instance in physics, different theories, or in chemistry, in psychology, T1 to Tn. And you have observed that theory, one of them, Tk, is among these alternative theories the so far empirically most successful theory. So by means of an epistemic inductive inference, you infer that Tk, the theory Tk, is the most empirically adequate theory, right? So this entails, of course, that you expect that Tk will also be in the future most empirically successful among these. So you trust Tk more than the others, and you use Tk as a basis of your predictions, right? You use Newtonian physics and not Aristotelian physics, because Newtonian physics is explanatory much more successful in order to predict the trajectory of a rocket or a Skylab or a space shuttle or whatever. This is one step, and I call this an instrumentalist conclusion, because what this commits me as for instance, from a philosophical viewpoint, is to believe in the reality of the empirical part of our theories, and the belief in the reality of the empirical content and the empirical success, but not necessarily that the theory Tk is also the theoretical part of the theory, the theoretical model is also true in the realistic sense, right? This is the next step. This abductive step, which I just explained before, namely to infer from the fact that the theory Tk, by means of an induction, is the most empirically adequate theory among all competitors, that it is probably true, or at least approximately true in the realistic sense. This is an abductive inference step, right? And this is typically what the so-called realists in philosophy of science propose, to go with the second inference step to go further and to infer the realistic truth-likeness of the theory. Now, for instance, Hilary Putnam in his no miracles argument argued generally, right, that it would be a sheer miracle if a theory is empirically adequate but not close to the truth. And so he argued for the inference to the truth-likeness of the theory. But what I have here is a weaker claim, which may be also called a minimal realism or a constructive realism, and which, for instance, has been proposed by Theo Kuipers from Groningen, and which is the position which I would absolutely subscribe here, that what Putnam does is too much, but what we can really do is this. It follows from the insights of Popper's critique, right, of logical inductivism, which we discussed yesterday, namely that we cannot really infer that the theory's truth-likeness are probably in some absolute sense, so in some sense of 90%, right? Because it could well be that in the future there comes a new theory unknown to us, unconceivable to us for now being, and this new theory is so totally superior that the old theory is no longer believed to be truth-like. But what we can say is we can also at the realistic level, we can make comparative statements. We can say that the theory TK is more truth-like than these competitor theories, right? We can infer from the superiority in empirical success and empirical adequacy the superiority of TK concerning its truth-likeness. That is what we really can say, and this is what I call constructive realism, the inference which constructive realism would go with, and that is what is really important when scientists speak about realism, and they say, well, I believe that this theory is closer to the truth than all competitors which you have discussed so far. Okay, so this is a picture. And with this picture, finally, you can also discriminate instrumentalism and realism in philosophy of science. These positions where I should say, in contemporary philosophy of science, I would say the majority of philosophy of science would go for a realistic position, but several for them are cautious and defend an instrumentalistic position. The difference can be explained as follows. Instrumentalists would say, just go for this inference. Just make assertions about empirical adequacy of theories, and not realistic truth-likeness concerning the theoretical part of the theories, right? Instrumentalists in this characterization believe in the empirical part of the theory in a realistic manner, but concerning the theoretical concept and all this mathematical machinery like forces, force fields, electric fields, magnetic fields, they think of that as an instrument to make successful predictions, but not necessarily as a model which is close to the true ontic structure of the real world. For instance, Van Fraasen is an instrumentalist in this sense. And there are different kinds of versions of instrumentalists, but what is common to them is that they just go for this inference, are skeptical towards this inference. While all realists go for this inference, right? They additionally recommend to infer from the empirical success the realistic truth-likeness of a theory, and again there are then different versions, and this which I have here is just a minimal version. Okay, so far concerning the interaction of induction and abduction in science. Any questions to that? Yes?
Usually one would say that an abduction has to be an inference to a more general theory which makes additional predictions to what you want to explain.
Yes.
So how is this the case with the abduction to realism, or to the realism of the theory?
Well, this is contained in this notion of empirical adequateness, and in this notion of empirical success, right? In the notion of empirical success, if you have to deal with theories containing latent variables or theoretical concept, it has to be inbuilt. If you go with that, I would agree to that. Use novel evidences, right? Evidences which has not been used for constructing the theory, count much more for the confirmation or for the assessment of the theoretical of the probability of the theory than evidences which have been explained post facto. That is clear. Right. So that concept goes already into this notion of empirical success, and then if TK is most empirically successful, you infer it's the most empirically adequate theory. Of course, this step is uncertain. It's preliminary. Of course, it depends on the state of the evidence. If new evidence comes in, maybe different. Of course, if a new theory is invented, the judgment is again different. I said that yesterday, last time when I had the last lecture, and well, but Van Fraassen would stop here. Van Fraassen would say, well, it's possible that the theory is close to the truth, but we have no epistemic means. That is not epistemically accessible, this inference. While realists would say, well, no, it's epistemically accessible. We are justified in making this inference. Yeah. Okay.
Right, but the problem I'm having with abductive inference is that usually this would mean that 3 has to make additional predictions.
No, that does not mean at all that.
Okay.
No, that is not the case. That is already contained here. If DK is most empirically successful, it has to make additional predictions compared to that. This is just a question whether you go for a realistic conclusion or not. That has nothing to do with that. Right? Yeah.
Just to add on, I mean, also you presented in your book so that inductive inference is some kind of, you use the same concept, but you generalize more. It's like here in the second step.
Yes.
And in the abductive inference, you also introduce new concepts that
like force,
theoretical, and they must not be empirical ones. So
yes. So here you may say, well, maybe there is no gravitational force. We don't know the essence of the gravitational force. Maybe there is no one. It's an effect of quantum mechanical interaction, or there is another thing going on which leads to this effect. Here you say, I believe that there is really something in nature which is the gravitational force, and which is approximately, right, to a certain degree, expressed by Newtonian or by our equations describing this gravitational force. Right? Yeah. Good. So then, thank you for this question. I go on. So this actually finishes the first part of my lecture, and I come now to the second part of my lecture. In my book it's called The Conceptual Toolkits. The Conceptual Toolkit, and what I mean by that is the logical foundations of philosophy of science. It is important to know, in order to assess the epistemic value of a sentence, a hypothesis, to know which logical kind it belongs to, right? Which is its logical nature. So we need a classification of sentences in order to say an interesting thing about confirmation, etc. Like, is it a general sentence? Is it a statistical sentence? Is it a particular sentence? Depending on that, it can be either falsified or not strictly falsified, but only weakened, and so on. But sentences are built up from concepts. And so therefore, in order to classify sentences, which we will do in the next lecture, we have to classify concepts. And this will be done in the remaining part of this lecture. Classifications of concepts as they occur in science. Of course, you have no question, no?
No.
Something like that. Of course, if you go, for instance, in linguistics, there are various classifications of concepts which are not in the center of logical classifications, because logical classifications are interested in certain things, but philosophical classifications in general are interested just in certain aspects of the concepts which are important for their epistemic There are three ways in which concepts can be classified. First, according to their logical type. Second, according to their content type. And third, according to what I call their gradation type or scale type. I start with the classification of concepts according to their logical type, and this presentation will be shortened a little bit. So for logicians, as I said already, from the logical viewpoint, you are not interested in different, like the difference between pronomina and demonstrative pronomina and personal pronomina, or the difference between verbs, adverbs and adjectives and so on. That is not so important. Just some distinctions are of essential importance for the classification according to the logical type. And the most important first distinction is set between logical concepts and non-logical concepts. Non-logical concepts, so to speak, designate something in the world, which is really in the world. It may be an individual, it may be a property or whatever. It is in the world, in the concrete world. While logical concepts have a purely, and here I don't want to be too much circular, have a purely logical function. So they denote certain operations, structural operations, but they operations which you can be formed on what is in the world, but they are not in the world, right? So I remove this slide now totally and reveal what's behind. So let me go up to here. So for instance, predicates like colors. A red color is somewhere in the world, like here. There's a red color. And an individual like Nina sitting here, she's also in the world. And this chair is there. But you know, it's not something which is in the world. It's a logical operation, right? And that is the difference between non-logical concepts and logical concepts. Okay. Then among the non-logical concepts, the second important distinction in logic is between singular concepts or terms and general concepts. Singular concepps, they are usually called singular terms in formal philosophy of science or formal epistemology. But we can also call them singular concepts, no problem here. Designate a single individual, a particular individual, or a particular spatio-temporal location, or a particular situation. So in logic they are usually expressed by these small letters a, b. So in natural language, for instance, the proper names are singular terms like my name, Gerhard Schurz, or Peter Miller, or whatever. Pronomina, I, me, you. Demonstrative pronomina like, or demonstrative pronouns, to use the English word, like this chair, that table, and so on, that table, this blackboard here, and so on. These are all singular terms referring to particular individuals, right? I mean, individuals can be quite large, like our galaxy is also an individual, right? But what makes them an individual is that they occur only once. They exist only once. While general concepts refer to entities which can be, as you say, multiply exemplified. They are exemplified many times. For instance, table is a general term. There are many tables in the world out there. I don't know how many, and if you go for the whole time span, then potentially infinitely many tables. You know, so the general concept table is a generic concept. It is multiply exemplified, right? That is a difference here. And the general concepts are expressed by predicates. And ontologically, there's an important point here to be made. Ontologically, predicates, first of all, let us make this logical distinction. Of course, there are predicates which have only one place, one argument. They express properties or kind. That is explained here. You write them usually as FG, like this is blue. So Fx, if Fx stands for the, in logic it stands for the expression x is an f, where f is now a predicate, right? And there are two kinds of predicates. They may express properties or they may express kinds. That is ontologically important, this distinction. Properties or kinds. What is the difference? For instance, a kind term like tiger, right? There are many tigers, of course, but the individual exemplification of a tiger, of a kind predicate, is an individual. It's an ordinary individual, this tiger. While the individual exemplification of a property, right, of like blue, like say red, like this redness here, this is not an ordinary individual, this redness. This amplification is what philosophers have called a trope. So this redness, this blueness is not an ordinary individual, but a trope. This is an ontological difference. So a trope is not ontologically self-sustained, so to speak. It cannot exist. It hangs on an individual, so to speak. It clues on an individual, but it is not an individual in the ordinary sense. So much for the distinction between properties and kinds. So far we spoke about one-placed predicates. They have one argument place. So for instance, in logic you write it in that way. If A denotes a particular individual, like this table, then FA stands for A is an F. So for instance, this table is light brown. Or this pencil is red. Right? And in this way you can formalize, as you say, natural language sentences by means of logical, formalized sentences, logical formulas. There are also two-placed predicates. They denote relations. For instance, I am the father of my son, right? Or you are the sister of Peter. These are relations, sister of, right? Relations between two persons. There are also three or n-placed relations in general, right? So these are relation terms which you write then in logic in this way, R, X, Y. A final important kind of generic terms are function symbols. Function symbols are a little bit different than predicates. If you apply a predicate like F, for instance, is blue, to an individual like A, like this sky, then you get a sentence. This sky is blue. If a function symbol produces an implication to an individual, not a sentence, but another individual. Here's an example. You write in logic function symbols with small f or g letters, and for instance a function symbol is mother of, and the mother of Peter, for instance, the mother of A is an individual, B, right? So the mother of is a function symbol. In application to an individual, it produces an individual. More precisely, mother is a one-placed function symbols, but there are also two-placed function symbols, etc. Function symbols are scientifically even more important than predicates. So whenever you go to a more precise language, what you usually do is to transform predicates or relations into function symbols. That is an important finding of its own, which is part of our Düsseldorf frame research group. It's important for frame theorists and other linguistic fields too. Look, for instance, in mathematics, numbers, for instance, 1 plus 2 equals 3, plus is a function symbol, right? It applies to numbers. It is a two-place function symbols. The application of plus to 1 and 2 is 3, and you write this then usually in this infix notation. So all important mathematical concepts are function symbols, almost all. Of course, there are also mathematical relations, of course. So in all quantitative sciences, quantitative concepts are expressed by function symbols. For instance, mass in physics is a function symbol, right? A function symbol denoting a function which applies, right, to individuals. Say the mass is time independent and assigns to them a certain number, like 80, and a certain unit, like kilogram. So this pairs and the value of the function invocation to the particular individual. So far about function symbols, they are very important for scientific non-logical concepts. All these concepts denote entities in the world. Different with truth functionals, different with logical concepts. Logical concepts denote, so to speak, certain logical operations over non-logical entities or properties. And here brief classification of kinds of logical concepts which are important in philosophy of science. Different kinds of logical concepts. If you write down the logical principles, rules or axioms which they satisfy, you get to different kinds of logics. Truth functional sentence operators are the first layer, like not, and, the inclusive or, the if-then operation, all logical concepts. And the logic of these truth functional sentence operators is what is called propositional logic here, right? So if you go here, that is what you learn in so-called propositional logic, the rules and axioms, principles of these operations. Truth functional means that if I know the truth values of the arguments of a logical operations, like and, like A and B, if I know whether A and B are true or false or whatever, then I can compute from the truth values of the arguments the truth value of the complex formula. That means truth functional. Then the next step is quantifiers. Quantifiers, you know, so it's obvious the truth functional operations are basic for all communication, right? So you need the and because the world is diversified. This is true, and this and this. You need the negation because some judgments are wrong, and then you say, no, that's not the case, and so on. You need the or because often you have choices, and so on. The next layer is quantifiers. You need also quantifiers absolutely in all kinds of everyday life. Like, for instance, if a mother tells her child of a primitive tribe, tells her children, well, this kind of plant is eatable. This is the universal quantification. All plants which look like this, you can eat them. How often of these plants and how many of them you will meet in the future, you can eat them. That's a universal quantification. So whenever you make an assertion about a domain, saying that all individuals of this domain have a certain property, without knowing how many individuals this domain consists of, that's always the case when you speak about future, then you need quantifiers. So the two quantifiers in first order logic are, or in predicate logic are, for all and exists. And the logic describing these quantifiers is called predicate logic. If the quantifiers are so-called first order, it's called first order logic, but I don't speak now too much about logics because this is philosophy of science and I want to go on. But just here, what is the notation here? If you write for all x, fx, this says all individuals x are f's, right? So the universal expression for all x, fx. That's how you read it. Or if you say all f's are g's, you write that in logic down as for all x, if x is an f, then x is a g, and so on. So this is how you need and how you use quantifiers, and similar for like the existing x, fx, some x's are f's, right? Would you express in that way? Okay. So much about quantifiers. As I said, the logic of quantifiers makes up predicate logic, and with truth operations here, truth function operations and quantifiers, really you can already, you can define the whole set theory, and therefore the whole system of mathematics purely with these symbols, with this kind of logical symbols. Therefore these logical symbols are the most important ones in science. There are other kind of symbols. For instance, intentional sentence operators, for instance, necessary or possible, are usually conceived as logical symbols, which is only correct if necessary is meant as some kind of logical necessity. There's a controversy about that, about the nature of the operator necessity, right? If it's not logical necessity, it's not clear whether it's really a logical symbol. Or probable is an intentional sentence operator, probability. And then, of course, a final kind of logical symbols, which I have already used a lot of times, are variables. Variables have to be used in combination with quantifiers, right? If you speak about all individuals of a domain, you don't know about which concrete individuals you speak, but you need a variable, an x, which ranges, as you say, over these particular individuals, which you don't know, right? But what you know is all individuals x, right, in this domain satisfy the condition that if they are an F, they are G. So all ravens are black, even if I don't know all ravens, I don't even know 5% of all ravens, I know only a few ones, right? But all humans, so to speak, all living organisms have a finite lifetime, right? This is a very general law of nature. Nobody has an idea how many living organisms exist in our galaxy, but this is a claim. All living organisms have a finite lifetime. This is typical for laws of nature, and you see that quantifiers and variables here are of essential importance to formulate these general expressions. So far about the logical kinds of concepts. Mathematical concepts like concepts of set theory, of arithmetics, also belong to logical concepts in a more general sense. Okay, any questions to this part? Which is more or less straightforward. If not, then I go on to the next classification, which is, so to speak, a classification which is more typical for philosophy of science. The logic classification is something which you also learn in logic courses. But just a point, a final point. Why do you need this in philosophy of science? Why do you need logic and logical formalization in philosophy of science? I give you a reason here. Because reconstructing the logical structure of a statement may be really needed in order to find out the nature of the procedures of commutability or of empirical test of the statement. Think about the statement, all substances have a melting point. Okay? Think about this law hypothesis. So according to Popper, and this is well known, universal statements cannot be verified. We will hear that in later part of this lecture, is the exact reason. Cannot be verified, but they can be falsified. Because finding one counterexample is enough to refute the universal statement. So you might think that this sentence can be falsified. No. look at what is its structure. There is an implicit existential quantifier hidden in this sentence. For all substance, there exists a temperature. For all substances, there exists a temperature T. So let's call this tau, so that X melts at tau, right? Or formally for all S, there exists a tau such that M melts at tau, right? In a brief notation here, right? You could, yeah. So this, all substances have a melting point, is not a purely universal formula, but a universal existential formula. And it's well known from logic that universal existential formulas are not even falsifiable in the strict sense, right? Because you never know how high this temperature may be. So this example shows you that really logically, why, not all, but many philosophers of science use to a more or lesser degree, of course, logic in explicating their methods, because it's just needed. It's not needed everywhere, and we know the logic fans as because logic is an art, is an art per se. But we need logic in order to find out about the nature of sentences like this, right? And we find out by logical reconstruction, no, this is not a purely universal. This is a universal existential sentences, so it's not strictly falsifiable. Okay. I come to these differences between strict falsification and weakening in later parts. Okay, that's why we need logic in philosophy of science. But now I turn to the second classification of concepts. The second classification does not derive from logic, but it derives more from philosophy of science. It concerns only non-logical concepts. So we have already put logical concepts, we have spoken about them in the previous classification. Now we speak about non-logical concepts, and what is the first important division here is the division between what I call descriptive concepts and prescriptive concepts. That is the most important first thing. So maybe I hide this now in that way. Yeah. Why is that important? Of course, most scientific concepts are descriptive concepts, and that is what science is about. But we have spoken about the value neutrality requirement. So we have spoken about the demand that in order to be, so to speak, to follow the rules of scientific objectivity, we must separate our value judgments and our norm judgment from the scientific judgment, which are descriptive judgment. Descriptive means these judgments and the concepts involved in them describe the world as it is, right? This means descriptive. So concepts which are descriptive, like table, chair, force, individual descriptive concepts like Peter, general descriptive concepts like table, force field, they describe the world. Prescriptive concepts, so to speak, tell us how the world should be like. And they divide into norm concepts and value concepts. Actually, there are of course different theories about values and norms going around in ethics, right? But the division, it's a suggestion to subsume value and norm concepts under the notion of prescriptive concepts goes back to Richard Hare. In order to fulfill the demands of scientific objectivity, we have to separate prescriptive statements and therefore prescriptive concepts from the descriptive ones, and that's why this distinction is scientifically important. So how many norm concepts are there? Basically, I mean, there are of course different natural language expressions, but basically there are only three different norm concepts. Something is obligatory, or you have to do it, you must do it, something is permitted, so you're allowed to do it, and something is forbidden, actually, right? So these are the three basic normative operations which you don't only have in geontic logic, but also in the logic of law, right? So of course you have different kinds of obligations, right? But these are the obligations. Actually, even the three ones are not logically independent. Does any one of you know how they depend? You certainly know.
Permitted if not forbidden?
Yeah, for instance. Obligatory, something is forbidden if the negation is obligatory, and something is permitted if the negation is not obligatory, right? So that's a logical connection, which are then called geontic logic. So you see, there are only a few normative concepts which are really fundamental. Actually, I mean, only in the standard geontic logic, you really can reduce all of them to that one. But there are non-standard geontic logic where you can do that, where you cannot do that. In defeasible geontic logic, for instance, you have permitted and obligatory, not fully dependent on each other. Okay. What about value concepts? That is also interesting, right? For instance, you can of course say, well, how many value concepts are there? Well, obviously there are moral value concepts, right? That is the core of ethics. When there's aesthetic value concepts, something is morally good, someone has a good character, this was a good deed, right? Helping people is good, causing pain to people is bad, and so on, moral concepts. Aesthetic concepts like something is beautiful, something is ugly, etc. Aesthetic value concept, that is clear. But some people say, well, there are so many other values, like there are technological values, a car is a good car, right? There are the values of chemistry, of the chemistry, and like a substance is a nice organic substance or whatever. But there is a confusion. What we mean here with value concepts are just what one calls intrinsic values and not instrumental values, right? We are speaking here about intrinsic value concepts. So if I say a car is a good car, it's an instrumental value, it's good for a certain given purpose. It is what I called 2 units before a hypothetical value assertion. Something is a good car in respect to certain purposes which I just take for granted, but I'm not arguing for, right? Because someone might say, well, I'm anyhow against cars because cars pollute the air, so I don't like cars at all, but still it's a good car in respect to having a good brake, right? That is an instrumental value. But we are speaking only about they are reducible. Instrumental values are reducible. But we are speaking about irreducible values, intrinsic values, being good in its own. Right? This is an intrinsic, being good in its own. And I would say there are only 2 kinds of intrinsic value, moral ones and aesthetic ones. However that may be, what is important in this consideration is although there are only a few value concepts. I mean, there are moral and aesthetic value concepts, and the basic primitive value concepts are only something is good. This is a qualitative value concept, either morally good or aesthetically good. Beautiful, you say in this case. Something is better than, the comparative value concept, and the quantitative concept of a value. Something is good to a certain degree are, right? These are the 3 basic kinds of value concepts. Any questions so far? Yes?
You mean there are only intrinsic moral or aesthetic values that are non-epistemic?
Well, all moral and aesthetic values are non-epistemic.
But there are epistemic intrinsic values too.
Yeah.
And so
yes.
When you say there are only intrinsic values to the moral or aesthetic?
I mean the non-epistemic values, and I mean the non-epistemic norms. That is right. That is important. Thank you for this correction. I should have said that. Of course, I mean the value of truth is an epistemic value, and I mean, it's just what defines science.
But it's also an intrinsic one.
It's also well, that is controversial. That is controversial, and it's. I mean, you know, the epistemic nature of a value is just, in my view, it's just posited. Yeah? What makes it epistemic is science is defined as following the goal of truth. But when you now ask the question, I mean, that's a deep question. So far I circumvented it. But when you now ask the question, is truth an intrinsic value, or is truth just an instrumental value, but an instrumental value of a certain kind, namely of that kind that you can, if you know truth, you can use it really for all kinds of purposes. So it's instrumental almost for everything, not for everything, but for value. So these are the two viewpoints concerning the nature of truth. This controversy is again an ethical controversy, I say. It's not a controversy which is answerable by means of the model of the empirical sciences, right? It's a typical ethical controversy. So even that, yeah. So even it's also important to separate any kinds of value statements. All of the value statements about the value of truth should be separated from the descriptive statements. Of course, epistemic value statements have a particular function and a particular role in science, but they still should be separated from the descriptive statements, because it's, as your question shows why this is important. Because it would be just wrong to say that a scientist, qua-scientist, can answer the question to which extent truth is an intrinsic value. I mean, actually I can pain, I can do hurt to people if I tell them the truth about their illness or whatever. So where is here the boundary? That's typically an ethical question, and not answerable by means of like empirical medicine. Good question. Thank you. Good. Any further questions to that? If not, then I come to the major distinction now between empirical and theoretical concepts. This distinction is most important for philosophy of science, but it is also highly controversial. I used it again and again already. It's important for the philosophy of science, which I'm arguing for. It's important for many accounts of philosophy of science. But it's also controversial how strict or how clear, how context independent this borderline between empirical and theoretical concepts is. Empirical concepts divide into observation concepts, and observation concepts refer to entities or properties which are directly perceivable, observable by our ordinary biological senses under normal conditions of perception. That is the idea. So really we have here the notion of direct observation in mind. So direct not in the sense that we see the reality naked, that's nonsense, we know everything about cognitive psychology, but direct in the sense that it is what is going on in perception of under ordinary normal circumstances of adult people who have a normally developed brain and normally developed sense organs and so on. So it's a question of biology actually and psychology, what I mean with an observation concept, something which is directly perceivable. Now, if you have a clear characterization of this thing, of what is an observation concept, then we can extend the notion of empirical concepts by empirical disposition concepts. This extension is quite easy, because, and I will explain it later. For the time being, I speak about observation concepts and the difference between observation concepts and the theoretical concepts. So theoretical concepts like force, you cannot observe a force. You cannot observe a gravitational force. That's what I would say. And it's an illusion if you think you observe it. If you fall free, you are under the action of a gravitational force, but by general relativity theory you wouldn't feel it at all. Right? What you feel is a different thing. You feel the pressure. If something blocks, you are free fall, right? But you don't feel the gravitational force, so to speak. Of course, you can't see it and so on. So it's really something which is not observable. Once again, you cannot feel or cannot see a magnetic force, right? I mean, some people say that some kinds of magnetic forces can be felt or somehow. I mean, there are actually some animals can see, can perceive, can feel magnetic forces, but not humans. So the notion of bodies directly observable is a psychological and a biological notion here. It's dependent on the kind of organism. But it's very important that for every organism, what the organism can directly perceive is quite limited. He has only a few number of sense organs. So we can perceive light waves of a certain wavelength. We cannot perceive radio waves. I mean, we can indirectly measure them, or make them perceivable by means of radio radars and whatever. We cannot perceive ultraviolet light. We can indirectly experience it by its consequences. If our skin gets brown, but that's what we perceive then is the brown color of the skin, and not the ultraviolet light. So it's important in a certain sense. It is important for philosophy of science to have the distinction between what is directly observable and what is not directly observable, but what is indirectly inferred, because of this abductive inference, right? It makes a big difference if you observe only two variables, right? But you infer something, a theoretical model containing a third variable, like force, which is not in your observation space. This is called a latent variable in science also, and this is very important to have this distinction. So, and actually in all practical models you make this. We already made this distinction in classical physics. We spoke about the kinematical variables, as you call them, the variables about the movement of bodies, right? Movement. Kinematics is called in physics, and we infer from them to the forces. It's called in physics, it's called dynamics. So we make in classical physics we make the cut here. Generally in physical disciplines we make the cut here. What we can observe is where the body particle is, how fast it moves, in which direction it moves, etc. What we cannot observe is the force fields. Well, okay, some philosophers would now say, and now I come to the controversy, like Thomas Kuhn has argued in that way, of course, others, Hansen, many people, that no concept is absolutely theory-free. So, of course, concept of movement in physics, velocity of moving trajectories are dependent on at least some theories. What would you say? Which theory? Geometry, right? The theory of time metrization and the theory of Euclidean geometry are entering these kinematical variables in physics, right? So it's not absolutely theory-free, that's right. But I mean, you can say, well, this theory is an unproblematic background theory which is just presupposed, and the theory about forces is that theory which is in question and which is in test. So you can make the cut between observation concepts and theoretical concepts somewhere in a very plausible way. The question is there a notion of direct observation concept which is really, so to speak, generalizable, which is not pragmatic in some sense, which directly reflects what humans can perceive with their ordinary senses without presupposing any kind of theory? And I would say, well, yes, there's a positive answer to that. And the idea is already written down here. The criterion for observability, I would suggest, is ostensive learnability. So, of course, as I said, an observation concept is not absolutely theory-free. You might argue that even our brains have some inbuilt, genetically determined theories inbuilt, like theories of three-dimensional vision with Euclidean laws of projections having it inbuilt. So you might say there are some theories inbuilt into the visual center of our brain. But what I mean with theory here is not an inbuilt, genetically determined biological theory, but a learned theory. A theory which has been acquired in cultural evolution. And I argue that the criterion for observability should have the effect that the observation concepts are independent from those theories which humans have learned, from learned theories, right? And the criterion for this is ostensive learnability. An ostensive learning experiment is a learning experiment where you where a person learns the concepts by means of pure ostension. So you circumvent the influence of language in that respect. So for instance, you learn the concept orange. We know that certain cultures, for instance the Sunni Indians, do not possess the color concept orange. The question is orange an observation concept therefore? Is it an intersubjective observation? Can it be observed by all humans? And the answer is yes, because the Sunni Indians can learn the concept orange by means of an ostensive learning experiment. In an ostensive learning experiment you have a training set, you show them some examples of colors and you say this is orange, this is not orange, this is orange, this is all information which you give them. And you may have for orange, I mean orange is just an artificial word. It's an artificial word for the Sunni Indian. You don't explain them anything except you use this word. You could also write X instead of orange, right? So this is orange, this is not orange. So, and a concept is ostensibly learnable if after a few instances, like 20 instances or 30 instances in a training set, the person is able to understand what the concept means and is able to apply it correctly to a test set. The test set consists of examples where you ask the question, is this now orange, is this orange, is this orange? And if the person successfully answers these questions correctly, then the person has learned the concept orange by means of an ostensive learning experiment. And I argue that those concepts which are observation concepts in the narrow sense, here, which I have over here, are those concepts which can be learned by means of an ostensive learning experiment or by means of purely ostensive procedure. Right? And these concepts, I argue, I would say, are independent from all learned acquired theories, because these concepts are learnable by all humans, even humans from primitive tribes, right? They can be learned already by what is inbuilt, so to speak, in us as biological organisms, in our brains and in our sense organs, without independent from any theories which we have learned. So any questions so far to this suggestion?
I mean, what about for the ostensive training, you also need some kind of understanding of affirmation and negation and of pointing. You know the Quinian problem of identifying what is meant with pointing to objects and what is meant with affirmation and negation. This is some kind of background theory that is also assumed in ostensive learning.
Yeah, but I would say this is intersubjective, what is meant with pointing. That is, the basics of learning language is, as we know from studies in linguistics and biological anthropologists like Tomasello, that you have this joint attention procedure that you understand, the baby understands, if you point to that, this is a table, the baby understands that. If it would not understand pointing, then I mean, that's anthropologically universal for all humans. And it's also understandable what is meant by yes and no. Exactly right, that is assumed here. But I mean,
I don't think pointing is really necessary for an ostensive learning experiment. It could just be some way to confront the learner with this experience. It doesn't have to be pointing. You could put them in a room and maybe maybe there's a big screen and the screen turns orange, and then someone says, maybe there's a loudspeaker, someone says the word orange, and then the screen turns a different color and it says not orange or something like this. So the pointing isn't really necessary. It's just necessary that they somehow associate this experience with it.
Yeah, it's necessary that their attention is focused to the object whose properties have been learned and or should be learned. Exactly. Yeah. But I mean, the idea is here that you have a theoretical concept like say, an electron, or being visible by means of an electronic microscope. An electronic microscope that could never be learned by a native tribe. What is a gravitational force or an electric force could never be learned by a member of a native tribe, yeah? by an ostensive learning experiment. You would have to explain this person, first of all, our language, which contains already a lot of theory, then the standard theories of physics, right? And in order to successfully operate with an electron microscope. And a similar thing would go for a telescope, right? But it would be hardly possible to learn such a concept, a theoretical concept, by means of an ostensive learning experiment. That is the idea. Any further? Johannes? No?
Well, you haven't really spoken about the dispositional concept.
No, I've just spoken about that one so far. Yeah.
So, and I was wondering why you don't have a branching from theoretical concepts to dispositional theoretical concepts and non-dispositional ones.
Yeah, because almost all theoretical concepts are, well, because that is not so important. I introduce that later. But it's not so important, as we'll see. But I mean, one final objection, which no one of you put forward, but I would like to mention, is the continuity argument. The continuity argument is the objection that there is no, that even if you can make the distinction between observation concepts and theoretical concepts now in this clarified sense, there is no clear divide. The continuity argument has been, for instance, forwarded by Hempel and others, Maxwell, and it says that there's a continuous spectrum between seeing by the naked eye, seeing by glasses, seeing by light microscope, and seeing by an electronic microscope. Right. There's a continuous spectrum between that. So this kind of seeing is most theory loaded and cannot be understood without understanding a lot of theory. This kind of seeing is not theory loaded in my sense. Of course it may be loaded by inbuilt theories, by genetically determined theories, but that is another question. So also you see here that when I speak about direct observability, I do not assume that what is directly observable is a mirror of the nature of the world. Our direct observations may be wrong, so I don't have a kind of direct realism here. So when I speak of direct observation, that is important. I am not a defender of direct realism. I do not assume that we observe the world as it is, not at all. I'm just speaking, certain concepts reflect just what's going within our visual perceptual centers of our brain, and the outcome are observation sentences. But there you see there's a continuous spectrum. So seeing with glasses, is this already now, is that I have the glasses, does that mean that I do not directly observe you with the glasses? I mean, not really, right? So this influence is absolutely minor. I don't have to understand much about. There is not much theory involved in putting off your own glasses, but a little bit, of course, right? But if you go with a light, if you observe something with a light microscope or with a huge telescope, then already there's some theory involved, and so on. So this is fact that there is a continuous spectrum between directly observable and theoretical does not mean that there is a difference between the two. Van Fraassen once put the following argument, a nice comparison. He said that there's a continuous spectrum between poor people and rich people, but that does not mean that there is no divide between poor and rich, right? I mean, the similar it is for observable and theoretical. So far, yeah. And as I said, what is important is that the notion of something which is directly observable in this sense should not be confused with direct realism, right? We all know from cognitive psychology there are all kinds of optical illusions. So our senses may fail under certain conditions. I might have an illusion, right? I might have a completely wrong estimation of a distance and so on. It just means that it's independent from acquired, from learned theories. Okay. Now this last distinction, an empirical disposition concept goes beyond what you can observe by means of an inductive procedure. The difference is important here on the following reason. Classical empiricists like David Hume or John Locke thought that all scientifically worthwhile concepts, so to speak, could be reduced to observation concepts. That's certainly wrong. I mean, it cannot be done analytically. Later on, in the 19th and 20th century, there was a movement which is still strong today. They argued, well, that's not true, but we can reduce all concepts to empirical disposition concepts. This answers now your questions. These were the so-called operationalists, right? And I argue I belong to that party of philosophers of science who argue that even that is wrong, and you will see soon why. But let me explain now what is an empirical disposition concept. An example is X is soluble. Soluble in water, for instance. X is soluble in water. This is an empirical disposition. This means that you assert a temporal regularity. Whenever, so at any time, X is put into water, it will dissolve. Dissolve in it. 1 or 2 S? Anyway.
2.
Then let us write 2 here. Okay. Thanks. So it's an empirical regularity. When an empirical disposition means that whenever you put something under certain test conditions, a certain reaction will occur. The thing under test conditions will react in a certain way. So this is an inductive generalization over time, which you assign then as a disposition property to the object, like solubility in water, or other dispositions like elasticity, like the elasticity of a substance. You can stretch it, right, and it will regain its original shape. Elasticity. So these are disposition concepts, and of course they go beyond observation concepts in 2 senses. First, they explicitly involve induction over time, but secondly, what I can observe, I observe under so-called normal conditions of perception. These are the conditions under which my biological sense organs have evolved, like normal daylight, right? For the perceptive organ of seeing, right? Perceptive process of seeing. While whether something has a disposition like being soluble, solvability is only experienceable if I manipulate the reality. If I do something with the objects, I have to put the object into water in order to find out whether it is soluble or not. So this requires to go beyond the normal conditions. So disposition requires interaction with the world, so to speak, and that was what the operationalists, and the constructivists, always emphasized, that it's so important for scientists to get in interaction with the objects of their investigation, to put them under conditions, and so on. So this is an important difference here. So, now the question is, what is the difference between a theoretical concept and an empirical disposition concept? Not all philosophers of science agree here, but I think in science the difference is clear. And the difference is clear. Being solvable does not refer to a chemical structure. That would be a theoretical concept, a chemical structure. Having a certain chemical structure is a theoretical concept, right? Having a photophile structure, a polar bond, as you say in chemistry, with a positive and a negative, with a positive and a negative end of the electrically positive and electrically negative end of a chemical bond. That would be one chemical explanation of solvability. But that is not referred to by the empirical disposition concept. I mean, Quine, for instance, the famous philosopher Quine, suggested that this disposition concept should somehow refer to these theoretical structures, to these molecular structures. But I think this is dead end. This is not the right way. And the reason why these philosophers like Quine suggested that way was that they didn't like counterfactual statements, like law-like statements. They wanted to keep an extensional logic. But I think in science there is absolute agreement that the notion of solvability is independent from any molecular chemistry. I mean, the notion of solvability in water or in other liquids was known by chemists centuries ago, centuries before they discovered the existence of molecular structures. And it can be, it's perfectly understandable. Solvability is an empirical disposition concept. And it's defined in that way, that whenever you put the substance in water, it will be solved. Similar for elasticity. Like elasticity is an empirical disposition concept. The molecular explanation of elasticity, that is a theoretical concept and the theoretical model, right? And that is the difference here, which is important between empirical disposition concepts and theoretical concepts. Okay. So, this concludes my discussion of the classification of concepts according to their content type. Finally, I arrive now at the third kind of classification of concepts, which is also important in science. So that is now on. Namely, their classification according to what I call the gradation type or scale type. So this is my third classification. The classification of the gradation according to the gradation type rests on the fact that our world is not a digitalized computer world, so to speak, but properties in the natural world come in degrees, right? Something is not only heavy, its weight can be more or less, right? And most properties actually come in degrees. But not all. I mean, whether you are female or male, there's not such a question of degree. Maybe there is one. That's a matter of debate. Or whether whether you are a mammal or you are a bird, an organism is a mammal or a bird is not a matter of degree. So, in this dimension we can classify concepts generally in these groups. First of all, we have the qualitative concepts, and then we have the quantitative concepts. Quantitative concepts measure the degree in which a certain attribute or property, here you speak of an attribute, is realized by means of a certain number, right? I will speak about that soon. Qualitative concepts do not or not necessarily need numbers and numeric distances for expressing the property. And there we have the first important distinction. Classificatory concepts do not rank or order objects at all. Classificatory concepts are also called nominal or categorical scales. What they are doing is, given a domain of objects, right, a domain, they divide the objects into several subclasses. each subclass being a more or less natural kinds. For instance, the domain of vertebrates is divided in biology in mammals, birds, amphibians, right, reptiles, and fish. That is a classificatory scale. Humans are divided into females and males, and whatever fruits are divided into apples and oranges. These are classificatory scales. There is obviously no gradation here involved. I mean, apples are not more fruits than peas or whatever. Makes no sense. There are only two requirements which you impose on a classificatory scale. Namely, first of all, these divisions, the subclasses should really be disjoint. They should not overlap. Well, and that's already difficult enough. I mean, right? But that is solved by biological systematicists, as you call them in biology. Every animal which is a vertebrate should find itself uniquely in one of these fields. So there should not be animals which are both mammals and birds, right? For instance, fish, right? Whales or so on, do they belong to fish or mammals? That was a problem. But the disjointness requires that you either put them into the category of fish or you put them into the mammals. Aristotle put them into the fish category. Today biologists put them into the mammals because they have much more properties with other mammals in common with fish. So these are the typical problems which you have in classificatory scales. And the other thing is, of course, the classification should be what you call exhaustive. That is, the union of these subclasses should really exhaust every individual in the superclass. It should be, the union should be identical with the superclass. No, every animal should belong to one of these 5 categories. Okay. So let's go to the next kind of qualitative concept, ordinal ranking and ordinal scales. So for instance, I could here write down for you another classification which is used in social sciences: upper class, middle class, lower class. This might look just like a classifier scale, right? But if you look closer to it, you see that there's a certain gradation here. You speak of upper, middle, and lower. So, what is the criterion here? What would you say? I mean, depends, of course. It may be income, or whatever. It may be education. But some criterion is underlying this classification, which orders this in this respect. So whenever you have now a classification which is meant as an ordering, you speak of an ordinal scale. So when you have a domain of objects, an ordinal scale is saying that, well, you have objects of rank 1, rank 2, rank 3, and rank 4. And for instance, rank 1 are those objects which have the given property, for instance, in the highest degree, or maybe in the lowest degree. Just that can be read from upwards to downwards, or from downwards to upwards, as you want. So object of rank 1 are, say, have the property to the highest degree. So for instance, upper class, right? Most highest income. Object of degree of rank, not degree, of rank 2 have it to a lesser degree, of rank 3 still to a lesser degree, and rank 4 have it still to a lesser degree. That is an ordinal scale, or a ranking scale as you call it. For instance, in humanities and social sciences, attitudes of humans, attitudes or preferences are often represented by ordinal scales. For instance, how good do certain kinds of food taste for a person or for the average of a group of persons? Then rank them according to a given scale. Very good, tastes very good, like a steak or whatever, pudding or whatever. Moderately good, like potatoes or whatever, or salad. Tastes bad, like I don't know, a hard, an old bread or whatever. And tastes ugly, like, I don't know, whatever tastes ugly, like a frog or, I don't know, sticking fish, and so on. So that would be an ordinal scale. For instance, in chemistry you have an ordinal scale of the hardness of minerals, which is quite interesting. Here the ordinal scale is called the Mohs scale, and it is said that the hardness of talcum is 1, gypsum is 2, calcium is 3, and the hardest substance, solid substance which exists, has hardness 10, this is diamond, and hardness 9 is corundum. The criterion for this scale is that one mineral of a lower scale scratches the mineral of the higher scale scratches that of the lower scale, but not the other way around. But of course, if you have such a scale, what you not say is that the intervals between these two ranks have the same distance. This distance, delta 1, is the same as delta 2. You have no claim about this sort. Don't speak about distances. And that is a difference between an ordinal scale and the next kind of scale, which is called an interval scale. For in an interval scale, you really make the claim that these distances here between these ranks are the same, or stand in a certain relation to another, a numerical relation, usually just are the same. Like, if that would be 1 degree Celsius, 2 degrees Celsius, 3 degrees Celsius, then the interval, the distance between these temperatures would always be 1 degree Celsius, right? Which is defined at the 100th part of the temperature difference between the freezing point of water and the boiling point of water. That is 1 degree Celsius. And then you have to claim that this is an objective distance measure. But in ordinal scales you don't have any distance measure here. This is a real difference. It's clear in the Mohs scala for hardness that there is no objective difference, and it would be nonsensical to say that the difference in hardness between the diamond and talcum is 10 times of the difference in hardness between talcum and gypsum, right? That would make no sense. There would be no physical model for that. Would make no sense, right? No numerical model. But in an interval scale you make this assumption. So whenever you go now to really numerical measures, you are in the domain of quantitative concepts. And the two major kinds of quantitative concepts are interval scales or difference scales and ratio scales. So I briefly explain what is the difference between these two scales. In every scale, in every numerical scale, there are some conventions which are arbitrary. So which are not dictated by the physical structure of the world, but just set by us. So I start with the ratio scale. What is arbitrary in a ratio scale is just a choice of unit. Choice of the unit. An example of a ratio scale would be mass, volume, etc. So here in ratio scales you have an objective 0 point. So the 0 point is objectively given. Something has lower and lower mass and something has no mass at all. If there is no more matter, then its mass is 0, right? That is objectively given, like the volume. If someone gets smaller and smaller and then it disappears, volume is 0. Therefore, in a ratio scale, what is objective is of course not the absolute value. That my weight is 84 kilogram it makes no sense to say my weight is 85 because that depends on the unit. It's 85 kilogram, but you measure in gram, it's 85,000. So what is objective in ratio scales is a relation between two quantitative values, the relation between two magnitudes. So what is objective in ratio scales is that my weight is 85 times of the weight of 1 standard kilogram. That is objective, right? So therefore it is called ratio. So you can say in ratio scales a person who weighs 80 kilogram weighs objectively twice as much as a person who weighs 40 kilogram. Right? Therefore it's called a ratio scale. The relation, if you weigh say 40 kilogram, I know you weigh more, but you're really a thin person, so let's approximate it. If you weigh 40 and 80, then our relation 2 to 1 is independent from the choice of the unit, because the unit cancels out in the ratio. That's why it's called ratio scale. Now in an interval scale, something more is arbitrary convention. It's not only the choice of unit, which is conventional, but it's also the 0 point. Or in an interval scale, also the choice of the 0 point is conventional. And an example is degree Celsius, temperature, right? Temperature measured in degree of Celsius. So here we say, by convention we fix the 0 point of temperature to the freezing point of water, and the unit to 100th of the difference between the freezing point and the boiling point. And this is measured by the expansion of a mercury column, for instance, or by its expansion of some other kind of liquid substance which expands when heated. So what you can say here, you cannot say that 20 degrees Celsius is twice as much as 10 degrees Celsius. That's nonsense. The ratios are not objective. If you measure in Fahrenheit, Fahrenheit has the 0 Celsius point as 32 degree Fahrenheit, right? And 1 degree Fahrenheit is 5/9 of 1 degree Celsius. So 10 degree Celsius are something like 50 degree Fahrenheit or 52, I don't know, 50 I think, and 20 degree Celsius are 68 degree Fahrenheit, right? So, I mean, the relation of 68 to 50 is of course very different from the relation of 20 to 10. So you see, because the 0 point is conventional, that is not objective. But what is objective are the differences between measurement points, between measurements. So you can say the difference between 20 and 30 degrees is exactly twice as much as the difference between 10 and 30 degrees, and is exactly the same as the difference between 10 and 20 degrees. And that is also true for the Fahrenheit scale. So that means that the amount, if you know, for instance, is very important because you know the amount of caloric of heat which you need to increase the temperature in a closed system is proportional to the increase of temperature. You can say the amount of heat which you need to increase the temperature from 20 to 30 is twice as much as from 10 to 30, and that is invariant under all scales. So in interval scales, the ratio between the differences between measurement points, they are objective. And that is an important difference between these two numeric scales. In the next lecture, I will speak a little bit about that. I will conclude this section and then we'll come to the classification of statements. Thank you.